Hello, this is Mr. Sorrentino again, and I am continuing my video lectures on Math 31 with the last section in Chapter 4, which is 4.6, Polynomial and Rational Inequalities. We had already just had two different sections in previous chapters in solving inequalities. In the very first chapter, we solved very basic linear inequalities, and they basically were just like solving an equation, except we had to remember that when we multiplied or divided both sides of an inequality by a negative value, we had to switch around the inequality sign. When we started looking at situations dealing with absolute value inequalities, we started using a procedure where we solved a similar equation, found the solutions, and then used the number line to assist us in finding the actual solution, which we would typically describe and give in interval notation. This method is going to be very similar to that second method. The method of basically setting up a similar equation and then using a number line to assist you is a time saver. You just have to make sure that, one, if you're solving an inequality, the answer should end up being an inequality. We talked about a rare case here and there with absolute value inequalities that you may get a single value as a solution, but most of the time you're going to have intervals. There also will be instances where you may have special cases with this too. In those special cases, you have to be aware of the fact that if you end up with an equation that ends up having no solution in the end, when you solve the equation that's set up from the inequality you had, that means that you could either have, in fact, no solutions as well for the inequality, or everything could be a solution. So we're going to be using a very similar method to that, with the exception is that instead of just rewriting the equation with the inequality, being replaced with an equal sign, we're actually going to rearrange the inequality so we're basically solving one side for 0, and then we're going to turn that into an equation. Because being able to compare whether or not you're greater than 0, which means you're positive, or negative, which means you're less than 0, is quite easy. Whereas if you have to compare two different sides of the inequality, that can involve a great deal of work as well. So we're going to be looking at a procedure here that you're going to be following when we do this. So to talk about this procedure, let's kind of walk through it here. You're going to manipulate the inequality so one side is equal to 0. I mentioned that before. So basically you're going to get one side of the inequality to be 0. So you're going to move everything accordingly. And this is going to be known as f of x. So this f of x can be a rational equation. It could be a rational function, a polynomial function, whatever the case may be. You want to solve an equivalent equation by setting f of x equal to 0 and finding the zeros. So you're going to find those zeros, which would be the solutions to the equation. You also, for rational functions, and this is important to note, for rational functions, you also want to find any domain restrictions. The reason is, if you remember the procedure we did for absolute value inequalities, once we found our solutions, we would put those on the number line, and that would split my number line into how many ever regions or sections, and I would basically test values from each of those sections to determine what's going on with the equation as a whole, or the inequality as a whole. We're going to be doing the same thing here. So when we find the zeros, those are going to obviously be points we want to test. But rational functions, if you go back and remember when we were graphing them in the previous lesson, which is why they went through that beforehand, if I have a rational function, let's say it has a vertical asymptote at 3, your graph could be doing something along the lines of this. And as you can see, although there's no 0 here, on a polynomial function, if I go from having a positive value to a negative value, the graph has to pass through it. So that's why we use the zeros for anything polynomial in nature. But I don't necessarily have to have, for rational functions, it pass through the x-axis for me to go from having positive y values to negative y values, because of the way that rational functions behave and split with their vertical asymptotes and having their horizontal or oblique asymptotes. So those domain restrictions, as we say in 3, the zeros and the domain restrictions are going to divide the x-axis into subintervals. And then once I figure out what those subintervals are, I'm going to pick a value from each of those subintervals, test them out, and see whether or not it makes f of x positive or negative. And depending on which one it is I'm looking for, state whether or not I'm going to shade a number line in that subinterval. And so we change the appearance of the number, and then we use that number line to write the solution to the inequality. So that's what I'm going to show in this video. Let's have a look at the first example and go from there. For example 1, part A, we're given this inequality: 4x plus 2 is less than 3 minus 2x squared. Having an x in an x term prevents me from using basic algebra to solve it. I mean, otherwise I wouldn't have to worry about, all the various circumstances. But when you start getting into quadratic inequalities, much like absolute value ones, start getting the polynomial ones, rational ones, that's when you start getting a lot of and or statements that work their way into the problem. And those get to be very time consuming if you follow some rules that are often taught in algebra textbooks and sometimes at the high school level. So I'm going to use the procedure that we were told to use. The very first thing I'm going to do is get this inequality to be, set to 0. So whether it's going to end up being less than 0 or greater than 0 is going to depend on what I have to do to both sides. So this one here, I'm going to subtract 3 from both sides. And I'm going to add 2x squared to both sides. And as a result, I end up with 2x squared plus 4x minus 1 being less than 0. Now it's a quadratic inequality. So now I'm going to convert this, and I'm going to change color with this because remember, I'm going to make a similar equation. It's going to be set equal to 0, and I'm going to solve this. And I'm going to solve this, in this case, using the quadratic formula. It's already set equal to 0 anyway. So I'm setting up the quadratic formula. Now I'm going to evaluate. I'm going to have 16 plus 8, which is 24. Which is going to have negative 4 plus or minus. I can factor a 4 out of there, which gives me a 2 square root of 6 in the long run. And so I could say I have negative 1 plus or minus square root of 6 over 2. Those are my two zeros. They're irrational. Not as easy to graph on a number line, but I could work with that. The calculator can certainly assist me in some ways with this, or just having a little bit of math knowledge could help me with this. But those are my two zeros. So I'm going to set up a number line because I got to now solve my inequality. Negative 1 plus the square root of 6 over 2 is about equal to 0.2247. So I'm going to note where 0 is, although it's not something I want to mark on my number line specifically. But I can say that negative 1 plus the square root of 6 over 2, and I'm just going to put in here, it's about 0.225, is over on this side. And of course, let's say there's a reason that negative 1 minus the square root of 6 over 2, it's starting negative and me subtracting more from it's going to be negative. If I carry through the subtraction, that's about negative 2.225. I want to keep note of that because of the fact that I want to know what kind of numbers are what numbers to be using, because what I want to do now is I want to pick some numbers from the three regions I have, because right now I have this in an open dot here, because remember, this value is going to make this inequality here. It's going to make the left-hand side equal 0. I don't want to equal 0. I want to be less than 0. Same thing here. Open dot. And I want to pick a value from each one of these subintervals. So I have 0 here. You might as well use it. It's already there. I'm going to pick 1 here. And here I'm going to pick negative 3. I could pick any numbers I want from these subintervals. I didn't have to use 0 in the middle one. I could have used -1. I could have used -2 for that middle region. Any one of them is a good representative, but all I need is one of them to evaluate what's going on here. And what's nice about this, because ultimately all I have to do is see if it's going to be positive or negative. So I may not even have to do a full calculation. Like for instance, if I use -3 here and plug it into this inequality, -3, I'm going to have 2 times 9, which is 18, plus 4 times -3, which is going to be -12. So I have basically here 18 minus 12, which is 6 minus 1, that's going to be positive. Well, I want it to be negative, so I'm not going to shade that region. I put 0 in. Those are easy. I always try to use 0 when I can, because anything with an x becomes 0, I'm left with -1. That's negative. So I am going to shade that. I do want to be less than 0, and that's going to be less than 0. If I had tried -2, or -1, or those would have given me values that were negative as well. So I plug 1 into this. 2 plus 4 is 6, minus 1 is 5. It's not less than 0. So what I have here is my number line, which describes my solution. And therefore my solution in interval notation is -1 minus the square root of 6 over 2 to -1 plus the square root of 6 over 2. Anything between those values is a solution. I could have also written it, if I'm not asked for interval notation, x is less than -1 plus square root of 6 over 2. Because remember, we're still looking for exact solutions to these. That could have also been the solution, writing it in as a standard inequality. It's an and statement. B and C are actually very similar problems, but they're actually representing a very specific situation. So let's look at those together, but yet separately. So let's kind of separate this a little bit. These are already set to having one side equaling 0. So I'm just going to start with that and say, okay, well, let's start with the similar equation. X squared plus x plus 9 equals 0. And if you go through the quadratic formula, my b value is 1, so -1 plus or minus the square root of 1 squared minus 4 times 1 times 9 all over 2 times 1. If you look at what's underneath the square root symbol, that discriminant, I'm going to have 1 minus 36. This is going to be negative, which means that there is no real solution. But remember, again, that is for the equation. So remember, when we do this, we're solving a similar equation. What does that mean for us? Well, for B, I'll use green for this one. Well, I'm going to set up number lines. In both cases, I would set up a number line where I don't have anything marked as any kind of answer on there, because the equation had no real solution. So I'm just going to pick a value. I'll pick 0. I'll do the same thing on this one. For this one here, if I use 0 and plug it into the left-hand side, I get 9. Is 9 greater than or equal to 0? Well, yes it is. So in this case, I would shade in the entire number line, because any number I pick from the number line is going to make that inequality true. So basically for B, because the similar equation had no real solution, this is going to have a solution of all real numbers. Or you could say x is any real number. Whereas in the other instance, if I go and plug 0 in and I have what I have in C, well, 9 is not less than or equal to 0, which means I'm not going to be able to have anything work for this. So this would have That's a simple VLP for no solution. You can just say no real solution. Something along those lines. So again, so we had this idea come up before with the absolute value inequalities. It's still going to be something that shows up here. So if you solve if you make your similar equation and get no real solution for the equation, that means the inequality may have no real solution as well, or it may have every real number as a solution. You have to look at the individual situation and test it accordingly. On to the next example. For example 2, this is a polynomial inequality. It's a degree 3. I mean, the quadratic ones we had before were polynomial inequalities themselves, but they were specifically quadratic. The quadratic formula can work its way into it. Here, I might be able to work the quadratic formula into it, but I'm going to have to, play around with things a little bit to make sure that I know what's going on with it and factor it accordingly in some way. The first thing we want to do is get this set to 0. So I'm going to take this inequality and I'm going to rewrite it, x cubed plus x squared minus 4x. I'm going to be subtracting 4 from both sides, so this side's going to have a minus 4. This is going to be greater than or equal to 0. Now I'm going to solve a similar equation. So I'm going to set up x cubed plus x squared minus 4x minus 4 equal to 0. I do have an even number of terms here, so it looks like it would be a good idea to at least attempt a group and factor. So I'm going to group these first two together. I'm going to group these next two together. And if I look at the first two, I can factor out an x squared, leaving me with an x plus 1 in here. And out of the second group, I can factor out a negative 4, which will also leave me with an x plus 1. I'm always trying to get that quantity to be the same, but if it doesn't work, it doesn't work. Sometimes it will not work, and you have to use some other method. Don't make it work if it's not meant to. Here it does, though, so we're lucky. So what I have here is x plus 1, which I can factor out of both of those groups. And when I do that, I'm left with x squared minus 4. That equals 0. So that means that either x plus 1 equals 0 or x squared minus 4 equals 0. Now you could have also at this point noticed that x squared minus 4 is a difference of squares, and you could have factored that even more and just said, then you had your 3 factors and you say, well, either the first factor is equal to 0, the second factor is equal to 0, the third factor, but it still works out the same in the long run. This one here, I subtract 1 from both sides, x equals negative 1 is my answer. Or here I'm going to have x squared equaling 4 when I add 4 to both sides. I put a square root into this, which means a plus or minus square root has to be put here. And so I'm going to have, as a result here, x equals plus or minus 2. So I have 3 solutions here to the equation. I have negative 2, negative 1, and 2. But again, that's the equation. That's not the inequalities answer. So now I have to go and use a number line to figure out what the inequalities answer is. So I'm going back to this one here, the one I have set to 0. I'm going to put the negative 2 there. I'm going to put the negative 1 there, and I'm going to put the positive 2 here. Notice I'm not really, these are not showing any kind of scale. Obviously negative 1 and negative 2 should be closer together than negative 1 and positive 2. I should have probably a longer interval between those two. I'm just setting up a number line to kind of know how it's segmented. I'm not really scaling this accurately, and I don't really need to. I just have to be aware of where things are with respect to each other, like which value is the smallest, which one's the largest, and so forth. Now, since negative 2, negative 1, and 2 are the values that would make this left-hand side over here equal 0, and of course make the original inequality, the left-hand side, equal to 4, those are going to be, those are part of the solution because I want greater than or equal to. So I'm going to put solid dots here, ones that are filled in, no holes, solid dots. As you can see, these 3 points split the number line into 4 different intervals, subintervals. So I need to pick representatives from each one. So I'm going to put a -3 here. That's the one I'm going to choose for this one. You can pick any other number that's smaller than -2. I picked -3. For -2 and -1, well, I have to say like -1.5. So here I have to use a decimal because I don't have any other integers between those two. Between -1 and 2, I have 0. I also have 1. I'm going to choose 0 because it's the easiest to work with. And of course, a value that's more than 2, I'm just going to use +3. And then I would go back. This is my f of x value. And I would figure out f of -3, f of -1.5, f of 0. So if I use the -3, I'm going to have -27 plus 9, which is -18, plus 12, which give me a -6, and then I'm going to have -4. That's going to be negative. So that's not greater than or equal to 0. So -3 doesn't work. So I'm going to say like f of -3 was less than 0, so that doesn't work. If I do f of -1.5, f of -1.5, that could, that's a little bit more problematic because, you have to do that calculation. I get 0.875, which is in fact greater than 0. That is going to make that inequality true. So, or f of x greater than or equal to 0, so I'm going to shade this in. At 0, 0 is always an easy one to use, so if you have the opportunity to use it as one of the representatives of their subintervals, that's a good one to use because everywhere there's an x, it becomes a 0. So f of 0 could be easily figured out to be -4, which is less than 0. So no, that's not going to get shaded in. F of 3, I'm going to have 27 plus 9, which is 36, minus 12, which is 24, minus 4, which is 20, which is greater than 0. That checks out. So I'm going to shade this. So when I state my solution, to the actual solution to the inequality, in interval notation, I could say it's from, now bracket, -2 to -1, or 2 to infinity. Or I could simply, if I write it in standard notation, I could say x is less than or equal to -1, but greater than or equal to -2, or x is greater than or equal to 2. If they have you address it in standard notation. Most of the time you're going to be asked for the interval notation, so make sure you know how to write that. Moving on to B of this example. So here's B, another cubic polynomial inequality. And I'm going to set it up first so that it is set to 0. So I'm basically going to subtract the 18x and add 5x squared to both sides. And when I do that, most of the time when you're dealing with the inequalities, it's going to be very factorable. It's going to be a rare occasion when it isn't. So a lot of grouping and factoring could probably be used for these types of problems. Not to say that every single one of them will be able to use that way. And if you find that grouping and factoring doesn't work, double check to make sure you're not making an error somewhere. But then you have to resort to some of the other techniques we talked about and made use of earlier. Grouping and factoring does work here, so I'm going to use it. If I group these together, these two and these two, the first two, I can factor out an x squared, leaving me with 2x plus 5 in here. The second group, I could factor out a -9, which leaves a 2x plus 5 left over as well. And I end up with the same thing. So I can say this is x squared minus 9 times 2x plus 5. Now, I didn't set the equation equal to, I didn't do an equation yet. I mean, I could do all this factoring on the one side as it is. But remember, I do want to solve the equation first. So I'm going to kind of do a side problem and say, okay, well, let's take the instance where this is the equation. Usually we did the factoring after we've established the equation, but you don't have to. But I do eventually just have to solve an equation. And for that to equal 0, either x squared minus 9 equals 0, or 2x plus 5 has to equal 0. If x squared minus 9 equals 0, that means that x squared equals 9. And if I square root both sides, that means that x would have to equal a plus or minus 3. Here I would subtract 5 from both sides. 2x would equal a -5, which means x would have to equal a -5 halves, which is the same thing as a -2.5. So there are the solutions to my equation. I want to solve the inequality, so I'm back up here again, and I'm focusing my attention on this. I have three solutions. I have -3, -2.5, and I have +3. These are the three solutions. Now, these are the three instances that makes this inequality up here equal to 0, the left-hand side equal to 0, or would be the instances that would make, the original, make the two sides equal to each other. I don't want them to be equal to each other, so these are going to be open circles. Now I'm going to choose some representatives from each of the regions that I have from these subintervals. So anything less than -3, well, I'm going to choose -4 as a representative for that. -3 and -2.5, -2.75 would be a good, or I can even just say -2.8, make my life a little easier. -2.5 to 3, I'm going to choose 0 because that would be in there somewhere, and one that's more than 3, 4. And with this being f of x, I'm going to put each one of these values into that function and see, well, I want the ones that are going to produce that, to make that negative. And so if I put in the -4, which is less than 0, so this one checks out. It's less than 0, so that means I'm going to shade that part of the number line in. I do the same thing for -2.8, which is greater than 0, so that's not going to be one of my answers here. Again, if I look at f of x, I put 0 in. That means all the things with x's become zeros. F of 0 is a -45, which is less than 0. And so that's what I want. 0 works, which means anything between -2.5 and 3 is going to work. And before you start saying, well, it seems like it's always alternating. In most cases, it will be, but it's not always going to be. So don't assume it is, because the moment you do assume it, you're going to find a situation where it's not going to be the case. So 4 doesn't work. It produces a value that's positive. We want values that are negative. And so it means anything to the right of 3 is not going to make f of x be negative or make the original inequality be true. And so that leads me to my solution. In interval notation, I could say my x's go from -infinity to negative 3, or they're between negative 2.5, which I could write as negative 5 halves, and 3. Or I could simply say it's, x is less than negative 3, or negative 2.5 is less than x, which is less than 3. With rational inequalities, one of the issues we often have to contend with is that, well, there's values of, I don't know what x is down here. X could be, can make x, I could pick a value of x that makes x plus 3 positive. I could pick those and make it negative. One of the things we do when we solve these is cross multiply. Well, when I cross multiply, if I multiply both sides by something that's positive, that's what cross multiplying do. If I'm doing the cross multiplication like this one here, that means essentially I'm multiplying both sides by that's x plus 3. Well, if I multiply both sides by x plus 3, if it's positive, nothing's going to happen to that inequality. If it's negative, it's going to change the inequality around, and that's going to start changing whether or not I, interpret it as an and statement or as an or statement. And that gets into a lot of different scenarios you have to try out and see what goes on and kind of, combine them together correctly. Problems like this could take up several pages of work to get to it to be done, if you use some of the other, some older methods for this. This method of solving a similar equation, it makes it much more streamlined. Now, when I do this for the rational inequalities, I kind of do it a little bit backwards first because of the fact that, a lot of times with these inequalities, they're going to, more times than not, they're going to give you inequalities that is just basically one rational expression greater than or equal to another rational expression. You may encounter a couple with an addition or subtraction, but you have to manipulate those in order to do the cross multiplication. But, the first thing but most of these I would want to do the cross multiplication. I'm not going to worry about setting it equal to 0 first. I'm going to set up a similar equation first and then eventually get it down to being one that's an inequality. Now, I still want to solve this for 0 or because I want to be able to compare positive or negative later. So, although I'm going to rewrite this one as x minus 4, x plus 3, minus x plus 2 over x minus 1, and set that equal to 0, I'm not going to manipulate this equation as it is, or turn this into an equation and manipulate it. What I am going to notice with this inequality, either the original or this one here, x cannot equal negative 3, and x cannot equal 1. Those would cause the denominators to be 0, and that means that part of this equation, part of this inequality wouldn't exist. Also, you have to remember, as I talked about before, these would usually indicate that I have vertical asymptotes, and vertical asymptotes, I can jump from being positive to negative around those. So, without passing through having a 0 in between. So these are going to end up being points that I have to consider on my number line. I haven't gotten to the point of needing one yet, but I have to keep in mind that eventually when I get to my number line, these are going to be a part of it. However, for as far as getting the solutions go, getting the things that either make this left-hand side of my altered one equal to 0 or make these two inequalities equal, I'm going to solve a similar equation this way, and I do that through cross multiplication. So when I cross multiply, I'm going to have x minus 4 times x minus 1 equal to x plus 3 times x plus 2. So I'm going to multiply these out. This is going to be x squared minus 5x plus 4. I'm simplifying as I move along, so you might have this written as x squared minus x minus 4x plus 4, and then of course the two middle terms become the minus 5x. Here I'm going to have x squared plus 5x minus or plus 6. When I solve these equations again, I want to get I mean, since it is quadratic in nature here, I want to get a set equal to 0. I would subtract x squared from both sides, and they would just simply cancel. These just go away. I'm going to add 5x to both sides. And I get 4 equals 10x minus or plus 6. I subtract 6 from both sides. I get that 10x equals negative 2, which means x is going to be equal to negative 2/10, which equals negative 1/5, which equals negative 0.2. Since all these are exact, I can write them in decimal or fraction form. It doesn't matter. But that gives me the one and only solution. So this is the only thing that's going to make these two original inequalities equal, I mean, these rational expressions equal to each other. It's also the one that's going to make this left-hand side equal 0. So when I go back to my inequality, negative 1/5 or negative 0.2 is a solution. It's a solution that's going to make the left-hand side equal to 0, and I'm allowing that to happen, so it's going to be a closed dot. Negative 3 and 1 are places where the graph could change from positive to negative without necessarily passing through a 0. So I'm going to put negative 3 and positive 1 on here, but they are going to be represented as open dots because of the fact that, I can't equal these values. We know this. They're domain restrictions. But I can go from being positive to negative. I can go from this expression here being positive or negative by jumping around those points. So I have these 3 points on my number line that are splitting the number line into 1, 2, 3, 4 subintervals. So I want to pick some representatives from each subinterval. Negative 4 would be a good one for this one. Between negative 0.2 and negative 3, negative 1 would be a good one. Between negative 0.2 and 1, 0 would be a good one. And after 1, we'll just say 2. This expression is our f of x. So I'm going to do each one of these and get an answer for it. Whenever I substitute the numbers I've chosen for my subintervals into the function f of x, which is the one I have set to 0. And so when I look at this, well, f of negative 4 produces 7.6, which is greater than 0, positive. And obviously that's not what I want. I want negative, so no. F of negative 1 is negative 2, which is less than 0. It is negative, so I want this one. So negative 1 works. It makes the inequality, it makes f of x less than or equal to 0. And so I'm going to shade this region in. For 0, I get a positive 0.6 repeat, or positive 2/3, which is greater than 0. So that's positive. I want negative, so that's gone. And f of 2 is negative 4.4, which is negative, which is what I want. So that does work. So the 2 and every number in that subinterval would also work and make f of x negative, which would also make the original inequality true. So that represents my solution for part A. And so my solution, and I'll write it in both ways. In interval notation, I would simply say that x is going from negative 3 to negative 1/5 with a bracket on the negative 1/5, because I could actually equal that, or from 1 to infinity. If I write it in standard notation, I could say negative 3 is less than x, which is less than or equal to negative 1/5, or x is greater than 1. So that's two ways to represent the solution, but as you can see, it's a very compact solution. And it only took me like a little area of a page to write the entire solution process out. Let's look at another one. Let's look at part B. For part B, again, I want to have an inequality that's set to 0. It's not going to be the one I do most of the math on, as far as manipulation to solve the inequality, but it is going to be one that I use to determine positive versus negative. So this here, I'm going to rewrite this as 3 over x squared minus 4 minus 5 times x squared plus 7x plus 10, and that's greater than 0. Because all I did was subtract the 5 over x squared plus 7x plus 10 from both sides of the inequality. This is what I'm going to be calling my f of x. And once I figure out values of x that I want to try out on my number line, this is what I'm going to eventually plug them into. But the other thing I have to look at with this is looking for those domain restrictions, because I want to solve the equation. I want to solve this equation in the long run. And again, I'm not really losing anything here, because if I would say, okay, if I wanted to solve my f of x and make a similar equation, what I would probably do immediately is add the 5 over x squared plus 7x plus 10 again to get to the point where I could do my cross multiplication. But any manipulation I'm doing is working under the assumption that these exist. And so I have to keep in mind that when I look at these functions, x squared minus 4 factors into x plus 2 and x minus 2. X squared plus 7x plus 10 factors into x plus 5 and x plus 2. So these do indeed, factor, and it does give me some domain restrictions. So I know as a part of my domain restrictions, x cannot equal negative 5, negative 2, or positive 2. Those will create zeros in the denominators of one or more of these rational expressions, and that means it won't exist, and therefore I wouldn't be able to solve anything. But now I'm ready to solve this equation down here, so I'm going to cross multiply. So if I go in this direction, I'm just going to basically have 3 times the x squared plus 7x plus 10, which is going to give me 3x squared plus 21x plus 30. I have to remember I'm distributing. And if I go in this direction, I'm going to have 5 times x squared minus 4, which is going to give me 5x squared minus 20. Now I want to get this set equal to 0, so I'm going to subtract 3x squared from both sides, subtract 21x from both sides, and subtract 30. So when I do that, I get 2x squared minus 21x minus 50. This is a quadratic equation set equal to 0, so now I'm going to use the quadratic formula and say, well, based on this, x is going to equal negative 21 minus the square root of negative 21 squared minus 4 times 2 times negative 50 all over 2 times 2. So that's going to give me 21. That should be a plus or minus. The plus didn't show up for whatever reason. Plus or minus the square root of, need to work this out, 841 all over 4. 841 is a perfect square. It's 29, so I have 21 plus or minus 29 all over 4. 21 plus 29 is 50. 50 divided by 4 is 12.5. I'll write it as a decimal since it's a terminating decimal. I'm not losing anything by writing it that way. Or 21 minus 29 is a negative 8. Negative 8 over 4 is a negative 2. Now, I'm going to throw out the negative 2 because it's extraneous. It's still going to end up on my number line though, because it's still a domain restriction, and domain restrictions will still end up on my number line as well. So, I mean, I'm just going to know it's not part of the solution, but it's still going to end up on my number line because it was a domain restriction. So even though I'm not expecting the graph to be 0 at that point, I can still possibly have a situation where I jump from a positive value of f of x to a negative immediately without passing through it because of the way that rational functions work. So now I'm going to set up my number line. The 12.5 I'm going to have on here, I'm going to note it. It's going to be an open circle there because I don't want anything to equal, I mean, that 12.5 is something that would make f of x here equal to 0. It would make the two sides equal to each other, which I don't want one to be equal to each other. I want one to be greater than the other. So it's going to be an open circle. I also have to include the negative 5, the negative 2, and the 2, because they're domain restrictions, and I can have that jump from positive to negative amongst them as well. And each one of those is going to be an open circle because I can't equal these things. I can only, jump around them, but they're all domain restrictions. So now I have 1, 2, 3, 4, 5 subintervals on my number line, and I need to come up with representatives from each one of those to test out. So one that's less than negative 5 would be negative 6. One between negative 5 and negative 2, I'll say negative 3. One between negative 2 and 2, good old 0, which is usually easier to work with. Between 2 and 12.5, I'm just going to choose 3. Keep the numbers as small as possible. And from 12.5 on, I'm just going to choose 13. And so what I want to do is figure out what each one of these are. So these are the values I get when I put these in. And again, I want the ones that are positive. So negative 3 works and 3 works. So that means that this region here is filled in and this region here is filled in. That represents my solution. So my solution is, again, I'm going to write it in both forms. I can write it in interval notation and just say it's from negative 5 to negative 2, or 2 to 12.5. Or I can simply say that, x is less than negative 2, more than negative 5, or 2 is less than x, which is less than 12.5. So these would be two ways to express the solution to this inequality. And that brings me to the end of this video. So this is the end of 4.6 and the end of chapter 4. So if you have any questions with this, please make sure to bring them up during class or come to see me during my office hours. Until I see you in one of those places or until the next video, have a good day and I will see you around.